Hello guys, so this video will be the last part of your chemical kinetics. Of course, in the overall chemical kinetics, we paid attention about the most important thing, that what will be the rate of a reaction. In simple words, that how fast your reaction can be. Although the chemical kinetics is just giving you that part in a very brief way. And we also came to know that in order to increase the rate of the reaction, what are the necessary factors which is going to influence your rate of the catalysis, so your rate of the reaction? It may be the concentration of your reactants. Yes, on increasing the concentration of the reactants, of course, we saw that your rate of the reaction also increases. It may be with respect to your temperature, and we also saw that with every 10 Kelvin rise in the temperature, the rate of the reaction nearly doubles or triples. Yes, and also we saw that with the influence of the catalyst, that catalyst also plays a vital role in increasing the rate of the reaction by reducing the magnitude of your activation energy. But the most important thing, what we saw in the temperature concept, that if a molecule has to react, they have to collide between themselves. Alva. So basically, when such a concept was arised, it was mainly given by a theory called as that of your collision theory. Collision theory. So from this collision theory, two important things we came to know that. First and the foremost thing, they are assuming that of your reacting molecules. The reacting molecules are of hard spheres. What they are considering, the reacting molecules are of hard spheres. Yes. And then what they said, if the molecules, whatever these hard spheres are there, if they are having the energy, yes, greater than or equal to that of your activation energy, then that collisions will give you the products. This was the two most important thing what is your collision theory states, which was proposed by Max Strauss and William Lewis. But here we have to keep a note point that overall collision theory is considering the reacting molecules as hard spheres. That was the reason when we took that of the concept of your concentration of the reactants. Of course, they were easy to explain that as the concentration of your reactant increases, what happens? The concentration of your hard spheres also increases. So when this concentration of the hard spheres increases, what happens? The collision increases. Product will be easily favored at a highest rate, of course. Then coming with respect to the temperature, what did they say? Yes, of course, on increasing the temperature, they are considering only the hard spheres. Do remember. So what happens? The collision between the hard spheres increases, which in turn results in that of your activated molecules, and the collisions between these activated molecules gives you the product. Alva. And most important thing, they said that, yes, whatever the number of collisions per second, per unit volume is called as a collision frequency. It's called as a collision frequency. So this was the most important thing. What does your collision theory explains that? If you are considering, for example, in a 1 meter cube, I'm taking it as a unit volume. In this unit volume, in 1 second, what collisions are happening, or how much collisions are happening, so that will be resulted as what? Your collision frequency. So number of the collision per second per unit volume is called as a collision frequency according to this collision theory. As per this theory, it also says that whatever your rate of reaction, rate constant is there, that is given by K is equals to Z times of AB into e to the power of minus EA divided by RT. So what is this Z of AB? If I am considering a bimolecular reaction A plus B give rise to this product P, whatever the collision frequency is there between this A and B, that is represented as a Z subscript AB. But we know according to that of your Arrhenius equation, what is that? According to Arrhenius equation, K is equals to what? A into e to the power of minus A by RT. Of course, when you are saying A and B, we can easily tally what? A is equals to Z of AB. Yes. So both will be the same. There also we saw that A was a collision frequency, but instead of A, collision theory is making use of a notation of Z. But as the collision theory is also stated that all the collisions does not give you the product. Alva, all the collisions does not end with a product. What did it say is, if a product has to be obtained between the collisions of your reactants, then those reactants should have a minimum energy called as that of your threshold energy. Alva. So the most important thing what that your collision theory explains that if the collisions has to give you the product, that means what? The colliding molecule should be having the threshold energy. Should have the threshold energy. This was the major important concept. Now, when we saw certain reactions, yes, I would be giving you an example. Of course, if you can just, I will be giving you the hint. We were dealing with that of your steric hindrance, if you are remembering. The same concept we are going to use over here. So when we saw certain reactions, we saw that even when we are increasing the concentration of the reactants, even when we using the temperature at a higher temperature, and also in the same reaction if you are using the catalyst, yes, the reaction rate is not get affecting much. Rate is not getting affected. So now the scientists were in dilemma. Yes, we know according to the chemical kinetics that if you are increasing the concentration, the rate has to be increased. If you are increasing the temperature, of course the rate has to be increased. And you are moreover, you are using a catalyst. It should be surely that your rate of the reaction should increase. But there were certain reactions. What were happening? Even I am using all the three scenarios which is increasing the rate of the reaction. What is happening? The rate of the reaction is not getting affected. In simple words, the rate is not increasing at all. Now there was a big question mark in the minds of the scientist. So what does that mean? Whatever we have learned so far was wrong. Of course not, because certain reactions are there. On increasing any of these three parameters, it is increasing. So they came to the conclusion that, of course, the collision theory is missing a concept. Is missing this concept, which is going to say further that how we can increase the rate of the reaction, which was a major drawback of your collision theory. And why this drawback came over here is because the collision theory mainly considered the reacting molecule as a hard spheres. Whatever may be, if you are taking Na, it is also a hard sphere. If you are taking a tertiary butyl, tertiary butanol, that is also a hard sphere. Is there not a difference between them? This was the major drawback your collision theory was having. It considered all the reacting molecules as a hard spheres. Why did they consider this one? Because it was easy for them when they considered the hard spheres to understand the collision between the reacting molecules. But that was not the scenario, overall scenario. Because when certain reactions were there, even though we are increasing all the three parameters, there was certain condition where rate of the reaction is not getting affected. So then the scientists came to a conclusion that there is another factor which is going to influence your rate of a reaction, which is called as proper orientation of the reacting molecules. Proper orientation of the reacting molecules. So what does it mean? What do you mean by this proper orientation? That means what? Of course, when you are using two reactants A plus B, instead of using or considering it as a sphere or simply blindly saying that your reactant is like a sphere, we have to consider its structure over there. and we have to study its structure first. That is, we have to study the structure of your reactants. That is, in case if it is a bulky group, how the groups are oriented, how the groups are surrounded, and when the groups are surrounded, whether that groups are having the higher electron density or whether they are having the lower electron density. In case if they are having the higher electron density, whether the incoming group is that is your another reactant, whether it is a nucleophile or an electrophile, and what is its structure. That was the main thing what another factor came into an existence, that was called as that of your proper orientation. So let us now understand this proper orientation by a simple structure. Okay, let us consider a structure over here. That is, let me consider a methyl bromide. Okay, that is C is in this way, H, H, H and a Br. Let me consider my A as that of your methyl bromide. What is this OH minus? Let it consider another reaction, a bimolecular reaction. Let me consider this one as B. Of course, what should happen now? The collision between the A and B should take place. If I consider with respect to the collision theory, of course they are the hard spheres. It will be similar to like that of your colliding of the two footballs when you are considering with respect to the collision theory. But of course, when you are using the collision theory, it is not going to explain that of your proper orientation because it is neglecting the structures. But proper orientation can only be explained by considering their structures. Now, what does it say? There are two scenarios over here. Okay, there are two scenarios. First is that of your improper orientation. Improper orientation. And another is that of your proper orientation. So what is happening? Of course, we know that this bromide ion is also a highly electron density molecule. It is also electron rich species. Okay, and coming nucleophile or an hydroxide ion is a nucleophile, which is also an electron rich species. It's a simple like your two magnets having the same pole colliding with each other. CH3, if I write over here H, H and a H, of course here is your Br. We know that this is having a delta minus, this is having a delta plus. Now we know that this is your delta minus. Now this OH minus, if it is coming and attacking the carbon from the way where your bromide is there, that is in this way, of course what happens, being the two same charges, they will repel from each other. Alva. So what happens? You are not going to get any product. So there will be no favorable for the formation of the product, or in simple words we can say that even though you are increasing all the three parameters, the rate of the reaction does not alter because it is not favoring the product at all. If I am going to select a proper orientation, of course what has happened knowing though, so whatever your Br is there, that will be on one side, and an incoming nucleophile, that is your OH minus, try to attack the carbon from that of your back side of your bromine, that is we can say an opposite side of your hydroxide. So what it forms, a temporary bond can be easily formed because it is avoiding the repulsion from that of your bromide. And what happens? A Walden inversion takes place, that we will be learning in your organic chemistry once again, the same reaction. Okay, what happens means whatever the structure is this CH3Br, it will be having an opposite structure when it's forming a methanol. That is what is happening means at an intermediate state will be obtained where your both hydroxide and bromide will be linked to your carbon. Of course, this intermediate state cannot be extracted. You can see it will be having a 5 bonds. So it cannot be easily, it is not such stable molecule. Highly unstable, so it will try to break this CBr bond. And when it breaks, you can just see the structure. Yes, here you will be having that of your OH, and see here you will be having that of your H, H and a H. Or simple words, this will be just an opposite image of that of the formed product. This is called as a Walden inversion. But major important thing you have to remember that when you're taking this reaction, this is the favorable step which is happening over there. That is, whatever your nucleophile is there, that is coming and attacking the carbon from that of your backside of the bromine. Why is it doing so? Because in a proper orientation, it leads to the formation of a bond. While in an improper orientation, what is happening? It is making the incoming nucleophile to bounce back due to the same charges. Please do remember, in my notes I have done it as a Br. Yes. So make it as over here as an OH, because we are getting the final product as that of your methanol, because bromide will be getting out, whereas your OH and comes and forms a bond. Please make it as that of your OH. Okay, CH3OH or methanol will be formed over here. Methanol. Okay, CH3OH plus Br minus. So this is what our collision theory is lacking to explain. So one of the most important thing we have to remember that in order to judge a rate of the reaction, we cannot simply say that it is only the temperature, it is not only the initial concentration of the reactants. But along with that, we have to also mention what? The proper orientation. Yes. So in order to get a product after an effective collision, we have to remember that along with the threshold energy, please mark my words, along with the threshold energy and another factor called as that of your probability or a steric factor or an orientation factor. So what they are saying means for an effective collision between the two reactants, till now what we were knowing that only threshold energy was enough. Only the threshold energy was enough. But now we have come to know that along with this threshold energy, in order to have the collision as an effective or a fruitful collision, we also need another factor which is called as that of your probability factor or a steric factor, or is sometimes also called as that of your orientation factor. Orientation factor, which is represented by the small letter P. P represents that of your orientation factor. Therefore, we come to the conclusion that so whatever our rate is there, it depends upon first and the important thing about that of your orientation factor. Then it is going to depend upon that of your collision frequency. That is what will be the number of the collision per second in a per unit volume. And then it is going to relate with that of your activation energy and that of your temperature. So this is the most important thing one has to know when you are dealing with that of your rate of the reaction. So in case if someone asks you what is the criteria for an effective collision according to the collision theory, you have to come across the concept that you have to know that one is that of your activation energy and another is that of your proper orientation. Why? Because when a collision happens, it is only possible to give the product if the two molecules are collided in a proper way. That is, the two molecule structures are oriented in a proper way. That is the reason, according to the collision theory, your probability factor and that of your activation energy are the two important criteria for a fruitful or an effective collision. Please do remember one of the most important things. So this is our final expression which is going to judge your rate of a reaction. Do remember this chemical kinetics is very much important. Why I am saying this? Because whenever the scientist is doing certain reactions, he will be well aware that the reaction should take place at a faster rate itself. We can't wait for nearly 1 to 2 months, not even for 2 to 5 days. We want the reaction to happen in an instant of time. And how we can do that instant of time? First and the foremost thing, we have seen the factors. The second most important thing, along with that factor, what the missing concept was there, that is with respect to that of your proper orientation. Even though you are having the reactants, but also on increasing the reactant concentration, on increasing the temperature, on increasing the catalyst, it is not increasing the rate of the reaction. Means what does it mean? whatever the collision is happening between the reactants are not in the proper orientation. In case if it is happening, it should come to your mind that the reaction, if you are choosing this reaction, of course this reaction takes place, but how it is taking place? By the attack of your OH minus from the backside of your bromide. Of course, this is the concept we have said in order to make you understand. So when you are reacting with your methyl bromide with that of your KOH, remember this reaction takes place. But how it is taking place, that is very important. Because whatever your nucleophile is there, that is coming and attacking your carbon from the backside of your bromide. And this is only understood when we are seeing its final structure. Because what was your reactant structure, it is quite the opposite what you have obtained in your product. That is the H bonds. If it were all the three bonds were towards the observer, remember the formed product bonds will be away from the observer. This is the main concept. And when they studied this structure, they came to know that, of course, there is another factor which is influencing your chemical kinetics, the rate of the reaction, that is your proper orientation. Very much important concept, because in our organic chemistry also, the haloalkanes and haloarenes, we are going to study this reaction once again under the name called as that of your SN1 mechanism. Why it is called as an SN1 mechanism means, remember, SN1 means it's a nucleophilic substitution reaction following the first order. Okay, sorry, this reaction is mainly called as that of your SN2 mechanism. SN2 mechanism, which means what? Nucleophilic substitution reaction of second order. Why it is called as a second order? Because you can just see that it is involving both the reactants. Alva, when we saw with respect to that of your methyl bromide, of course the slowest step was only involving the concentration of your methyl bromide. This was your slowest step, which was giving you the carbocation, and we considered only this reactant. And we saw that it was following a first order. Remember, when your methyl bromide was treated with that of your KOH, that is called as an SN1 reaction. That means what? N stands for your nucleophilic. Of course, alpha OH minus, which is coming and attacking, that is a nucleophile. Substitution. That is what is happening. Your bromide is getting substituted in both the case. Nucleophilic substitution, first order. Why first order? Because whatever the reactant you have chosen is only with respect to that of your methyl bromide. And that is also to the power of 1. But here in this case, when you are seeing, this was your tertiary butyl bromide. But when you are seeing with respect to that of your methyl bromide, what is happening? It is following an SN2 mechanism. That is nucleophilic substitution reaction following the second order. Why? Because it is only your elementary step, which is involving both the reactants. That is the reason we are calling it as an SN2 reaction. Very much important concept when you are dealing with that of your haloalkanes and haloarenes. We once again detailed learning about over there about SN1 and SN2, and I'm sure I'm going to ask you the question about this. Please do remember. This chemical kinetics, see, there also it plays a vital role, because there we are also studying as why it is called as an SN1, why it is called as an SN2. For example, if I'm going to write its rate expression, I would be writing it as rate is equals to K times of the concentration of both CH3, Br and that of your OH, having the first order for that of your methyl bromide. So it is having a SN2 reaction. But when I choose for this one, my tertiary butyl bromide, of course I have written earlier. Once again I am writing, it is only depending upon what? CH3 thrice Br, which is following your first order. Because why it is a first order? In complex reaction, the slowest step is only with respect to that of your ionization of your tertiary butyl bromide. Please do remember. So this chemical kinetics, whenever we are doing a reaction, it is very much important to understand that how to increase the rate of the reaction. Okay. So this completes the chemical kinetics. If there is any queries, you can please post me in my WhatsApp group.